PR is okay too.
So good morning, everybody. We will continue. Welcome back to the Masterclass Brazil. We will continue today with lecture 5 on propagation aspects. So in lectures 1 to 3, we discussed the signals, signal properties, how to estimate parameters based on these signals. Yesterday we started a little bit to move on to the signal processing in the receiver. So we discussed how can we acquire the satellite signal receiver, so perform a detection, whether the signal is received, and it's also performed in the same time. We also perform a parameter estimation, a coarse parameter estimation, to then initialize tracking. Tracking we will cover in the next lecture, lecture 6 in this afternoon. And today I want to, in the morning today,
Could you just stop 1 minute? I think we are here a problem with the microphone. The people are told that they have problem here. Let me see what happened. Just a second. Okay.
Hello, hello. Okay. Good. Okay, good. Then I will get closer to the microphone. Okay. Good. So today in the morning, we will discuss propagation aspects. So what happens to the signal between the satellite and the receiver, and what are the dominant effects? So we have some general introduction and motivation about that topic, and then I will discuss Doppler effect, ionosphere effects, troposphere effects, and multipath propagation. So yeah, this is the list of the effects that we have to consider when we talk about ranging, because we have to mitigate all these effects in the receiver or correct these effects when we want to do ranging to a satellite, because we would like to only use a direct signal that is propagating in vacuum. This would be the best case to do precise ranging. And as we now have these propagation effects, we have to correct either in the time delay estimate or later in the positioning. We have to correct these effects. First of all, I mean the satellite signal enters from outer space into the upper layers of the atmosphere, and the first thing that the signal passes is the ionosphere. Here we have a refraction effect usually, also in the troposphere. In the troposphere, which is below the ionosphere, this refraction effect is less prominent. So we have, and both layers, they add a certain delay in general. In the ionosphere, this delay dependence on the frequency is larger across the spectrum. In the troposphere, it's more, let's say, constant within the bandwidth, but adds another delay. And so we can see here, this is shown here in the graphic. So we have some divergence of the, because of this delay, we have some divergence here from the direct propagation to the refracted one, to the antenna. And then we also have multipath performance. So we have maybe reflections. There could be also obstructed signals. So the signal is not passing in its direct path to the receiver, but maybe through a multipath signal only. This also happens. But in general, we have multipath, so reflection from buildings in the surrounding environment, for example, of the antenna. And then we receive several copies of the signal, but slightly delayed and maybe with a different phase. And we will talk about these effects. On top of everything, the satellites are moving and maybe the receiver is also moving. So we also have the Doppler effect that we need to consider. And all of these effects are usually treated by models. So we introduce some models for this propagation effects to make our life easier to correct these effects. So yeah, we will start here with the passband signal model. So I will explain all these effects based on, because they are induced to the passband signal, and I will show how they translate to the baseband signal. So the passband signal of one satellite, we can write this, and we did that before, with S tilde of t is equal to the square root of 2 of the real part of S of t times the exponential function of j2 pi fct. And we end up then here with a signal where we have an in-phase component Si and a quadrature component SQ. And the equivalent baseband signal then can be given as S of t that is equal to Si and SQ. Yeah, in the following, we do not consider the free space loss. And I have to correct this. This in brackets is not, I will delete that because this is a link from my lecture at the university. I have a dedicated lecture on link budgets and payload effects, but we don't have time during this course to look into this. So I just give here the message that we don't consider the free space loss, but there is a loss in power that is dependent on the distance between the transmitter and the receiver, and you need to design your system such that the minimum desired received power is ensured at the receiver. The different effects are discussed separately, but in reality are to be considered in a cascaded form. So we discuss Doppler, discuss ionosphere, troposphere, and multipath. Yeah, so let's start with the Doppler effect. So the Doppler effect, or the Doppler shift, this is already a model, is the change in frequency or wavelength of a wave or other periodic event for an observer moving relative to its source. And we will first consider the case that the receiver, which is given here on the left-hand side with Rx, is moving towards the transmitter. Both of them could have a velocity, so the receiver has the velocity Vr and the transmitter has the velocity Vt, and we see here the wave has the velocity of the speed of light, so we consider propagation in vacuum. In case a receiver and a transmitter are moving towards each other, the shift between emitted frequency and observed frequency F tilde for an electromagnetic wave in vacuum can be given by this formula here. So we have F tilde is equivalent to the emitted frequency F, and then we multiply by this factor. And this factor is dependent on the velocities of the receiver, the velocity of the transmitter, and the velocity of the speed of the propagation of the wavefront. So the speed of light in our case. And we can reformulate this here and say, okay, we only consider the delta V here, which is the relative velocity between transmitter and receiver. Yeah, in case delta V is much, much smaller than C, this is our case, and delta V divided by C is even smaller than 1, we can write now that the F tilde is equivalent to F times, so this is from the previous slide, and this can be now approximated as delta V is much, much smaller than C by 1 divided by 1 minus delta V divided by C. And this can be given equivalently as the sum of n0 to infinity times, so F times the sum of n0 to infinity delta V divided by C to the power of n. And using now that 1 over 1 minus x is equivalent to this quadratic sum, in case x is smaller than 1, that's why it was important to define also, or to assume, or in our case, this is the case, in our application, this is the case that delta V is smaller than C, divided by C is smaller than 1. We can now use this approximation and we get to the case that delta tilde F, so the apparent frequency at the receiver is related to the frequency at the transmitter times 1 plus delta V divided by C, and thus the Doppler shift of this frequency. So now the Doppler shift FD can be given by F times delta V divided by C. So we can see that this Doppler shift is dependent on the relative velocity between receiver and transmitter. And it's a positive shift. So FD is positive in this case. If we now consider that the receiver and the transmitter are moving away from each other, the shift between emitted frequency F and observed frequency F tilde of an electromagnetic wave in vacuum can be then given by this equation. And we have here the scenario so that the velocities are pointing away from each other. So for receiver and transmitter are pointing away from each other, so they're moving away from each other while the transmitter is emitting this waveform with velocity c. We can now do the same approximations here, pretty much the same. So we have delta V much, much smaller than the speed of light. Delta V divided by C is smaller than 1. Then we can approximate this equation from the previous slide. Here. With F times 1 divided by 1 plus delta V, and this can be then approximated by F times N, the sum of N0 to infinity of minus 1 to the power of N times delta V divided by C to the power of N. And so we have used now 1 over 1 plus X is equivalent to this sum. And when we now consider that delta V is much, much smaller than C, we can approximate this sum just taking the first two terms of this sum as before. And then we have F times 1 minus delta V divided by C. And in the end, now the Doppler shift, so FD is then minus F times delta V divided by C. So we can, based on the relative movement of transmitter and receiver, we get either a positive or a negative Doppler shift, but this is only for one frequency. Yeah? Now, when we transmit a signal that has a certain frequency support, so has power spectral density over a bandwidth, the different frequencies of these power spectral densities, they will experience a different shift, right? Because the shift is dependent, the Doppler frequency is dependent on the original frequency. And so the higher this original frequency, the higher this shift for each frequency becomes. So what we experience is this effect, and it's like a dilatation effect. This is shown here below. So if we have the carrier frequency f of c and we have the Fourier transform S tilde of f, which is the Fourier transform of the passband signal, we can see that the lower frequencies of our bandwidth are shifted less than the higher frequencies. So it's a dilatation effect. It's not a constant shift of all the frequencies. And we can see here the Fourier pair that is implementing this dilatation effect. So we have, we can see here if we introduce the frequency shift on the right-hand side in the first equation, we have the Fourier transform of the passband signal, and then we implement here the Doppler shift. So either with, so the shift of the frequency given by the Doppler effect. And then we see on the left-hand side, we have a change in amplitude in time domain, and we have a change in the time. So we have also a dilatation effect in time. And we can rewrite this also with using A being equivalent to 1 over 1 plus minus delta V divided by C. And then we can clearly see what happens. So we have then a dilatation effect of A specified by A in the time domain and also in the frequency domain. And we have to take care of this, especially when the signals become more wideband. However, in most of the applications, we assume that the Doppler introduces a constant shift. But we have to keep in mind that this is a model. This is modeling the original effect is a dilatation effect. So, but we can now study what happens when we apply the Doppler effect and how this is affecting the baseband signal. So we first now discussed here how the Doppler effect is affecting the passband signal, and then what happens when we perform a down conversion. So on the left-hand side, you see here a model for the transmitter. So we have our SI of t and SQ of t, the in-phase and quadrature signal, modulated onto the carrier with carrier frequency fc of t, and this creates our passband signal S tilde of t. Then this passes through the channel. In our case here, we only have the Doppler effect. So at the receiver, we have the signal experiencing the Doppler effect. So this is then in time domain 1 over, so the signal that we receive is 1 over 1 plus minus delta Vc divided by C times S tilde of T divided by 1 plus minus delta V divided by C. And now we perform down conversion. Down conversion with an ideal low pass filter also. So we multiply this signal by square root of 2 cosine 2 pi fct in one branch, and the other branch with minus square root of 2 sinus of 2 pi fct, then pass it through a low pass filter. This is to filter out higher order harmonics that are created by this down conversion, by the multiplication with cosine and sine, and afterwards we receive the down converted in-phase and quadrature signal as Z1I and ZQ. Yeah, and we can derive the in-phase and quadrature component of the baseband received signal now as Zi and ZQ. I use now again this form, the notation with A, where A is equivalent of 1 divided by 1 plus minus delta V divided by C. So we get these two components after the low pass filter. And we can see we have here the Doppler effect, this dilatation effect in the carrier signals and also in the baseband signals. And we can then write now that zi of t plus j cq of t, and we get to this formulation that a, the absolute value a of CIAT to the power multiplied with the exponential function to the power of j2 pi fct times a minus 1 plus j a absolute value of a sq a of t exponential function with the argument j2 pi fct a minus 1. And we can further reformulate this to the next line, and then we do the approximation here. We approximate now that 1 plus minus delta V divided by C is approximately 1. And if we do that, in our case, it's maybe okay, right? So the relative velocity is much, much smaller than the speed of light. So this delta V divided by C is maybe very small. And then we arrive exactly at, when we do that approximation, we arrive exactly at this model that most of us have in our heads, which is that we arrive at a constant frequency shift of the spectrum of the signal, but only after this approximation. So I want to stress this again. However, this approximation is only valid if and only if 1 plus minus delta V divided by C is approximately 1. And the observation interval of the signal is short enough. So we have to be aware of this, that the model that most of engineers deal with in signal processing usually is a model is based on an approximation here, and that the original Doppler effect has a dilatation effect. And especially when we deal with wideband signal, we could think about correcting the Doppler effect in a different way. But usually it's very complicated because you have to reverse this dilatation effect in the signal. But yeah, it could get you higher quality observations in your receiver. Yeah, let's move on now from the Doppler effect to the ionosphere. And let's see how the ionosphere is affecting our signal. So the ionosphere is a shell of electrons, electrically charged atoms and molecules that surrounds the Earth, stretching from a height of 50 to 1,000 kilometers. Ultraviolet radiation of the sun breaks the bonds relating the electrons to the atoms when transferring the upper atmosphere, so the ionosphere. Thus, there is a large number of free electrons and ions in the ionosphere. The free electrons in the ionosphere affect propagation of the radio waves then. And particularly ionized gas is called plasma. So that's where you read then in the literature a lot, people talk about plasma in the ionosphere. At frequencies below about 30 megahertz, the ionosphere acts like a mirror reflecting radio waves back to Earth. And this is used in some applications for long distance communication, because when you choose a frequency below 30 megahertz, you can quasi communicate around the world. And this is also done by radio amateurs. They try to reach people in Australia, or on the, for us, Australia is on the other side of the Earth. So they try to reach people, and there's a rich culture doing this. There's also some systems, for example, submarine communication is done by this. So if the base in the US wants to reach its submarines, they use a system like this. So you can communicate around the world. The speed of a radio wave in the ionosphere is determined by the density of the electrons. Then, if you choose a frequency higher than 30 megahertz to exit Earth, and also from the outside when you want to pass through the ionosphere, so the The speed is determined by the density of the electrons, and the electron density is quantified by counting the number of electrons in a vertical column with a cross-sectional area of 1 square meter. And when we do this, so we calculate all the electrons along the ray path of our signal, the propagation path, and this number in a cross sectional area of 1 square meter. This number is called total electron content. It's called TEC. TEC is a function of the amount of incident solar radiation, because the solar radiation breaks up the ions and electrons in the ionosphere. TEC above here on the night side of Earth, free electrons have a tendency then to recombine with ions. So when we have no solar radiation hitting the atmosphere, the ions and electrons, they tend to recombine. And this is thus then in the night, we see that the TEC is reducing a lot. TEC above a particular location of the Earth has a strong diurnal variation also. So during the day, also has variation from during over the seasons, over the year. This depends also how the Earth is relatively located. The attitude of the Earth is to the sun, and so on. Changes in the TEC can also occur on much shorter time scales. One of the phenomena responsible for such changes is the traveling ionosphere disturbance, TID. TIDs are manifestations of waves in the upper atmosphere believed to be caused in part by severe weather fronts and volcanic eruptions. And there's some work on using GNSS receivers to detect volcanic eruptions based on these TIDs, and also to predict the eruption before you can see it physically. So this is quite nice. There are also seasonal variations in TEC, as I mentioned, and variations that follow the sun's 27-day rotational period and the 11-year cycle of the solar activity. We are approaching, in this 11-year cycle, we are approaching a maximum again. So we are in the increasing, let's say, years of the solar activity. And so in a couple of years, we will again reach the maximum of the solar activity, which gives us, especially here in Brazil, a lot of disturbance in because of the ionosphere of the GNSS signals. This is showing as a small graph showing the layers of the ionosphere, and we see on the x-axis we have the plasma density in electrons per cubic centimeter, and we have on the y-axis we have the altitude in kilometers. So we see there are several layers, the D region, E region, F1, F2. They only exist during the day when we have sunlight. So when we have the solar radiation breaking up ions, so the molecules in ions and electrons. And we can see in blue, we have the layers in the night. We quasi have only the F layer in the night. And this is going from 125 to 1000 kilometers. The peak electron density at 200 to 400 kilometers, as we can see. And in the day, we have the D region that goes from 50 to 90 kilometers, very low electron density, as we can see, and from the E region, this is given from 90 to 125 kilometers. this vanishes rapidly after dark, but during the day, we have here at least some electron density. Yeah, the propagation of the signal through the ionosphere can be approximated by the transfer function hi, ionosphere, f, dependent on f. And we can see here that we have a delay ti of f that is dependent, this is dependent on the frequency. And we have a delay of the signal in vacuum. So this transfer function models the propagation of the signal in vacuum plus the effect of the ionosphere. And attenuation, so this AI is an attenuation of the signal. However, the attenuation of the signal is negligible for frequencies way above 30 megahertz. So in our case, we are at 1.5, 1.4 to 1.1 to 1.6 gigahertz. I think we are way above 30 megahertz, so the amplitude response in our case is not really important or prominent. So the amplitude AI in our case is maybe 1. In a first order approximation, we can write that this Ti, which is dependent on F, is approximately Re times C to the power of 2 divided by pi. And then we have this integral of the electron density along the ray path, L. This is then the tech value in our case. And so the electron density we have here, Re is the electron radius, so the radius of one electron. C is the speed of light, and we can approximate this with this number because the electron radius and the is known, the speed of light is known, and then we can approximate this with 40.3 times cubic meters divided by seconds squares. And the integral of NE along the ray path I defines and this is not this is what's called the slant tech, because it is along the ray path in units of tech, and they call this is then U tech, and this is 10 to the 16th electrons per square meter. So this Ti we can calculate, it's dependent on the frequency, but also on the S-tech, so the slant tech, the slant total electron content. I calculated this here based on this formula. We can see a little bit how this is dependent on the frequency, and I only use the frequency range in L-band, which is relevant for GNSS, so from 1 gigahertz to 1.6 gigahertz. And here, this is the phase delay that we can see here for different values of tech units, so 10, 20, 50, and 100. So we see if the ionosphere activity is stronger, we have a significant change of the delay over the frequency. This we will see in the following that this can be used to measure also the ionospheric delay of our signals when we do a dual frequency measurement, and we take into account this dependency over frequency. We can measure also the delay of the ionosphere. Now let's apply this transfer function again to our signal. So we have on the left-hand side again the transmitter. On the right-hand side we have the receiver doing down conversion. In the center, you can see that we have the transmitted passband signal S tilde of t, and we have on the receiver side the Fourier transform of this passband signal times the transfer function of the ionosphere. This time I wrote it in frequency domain because we define the transfer function of the ionosphere in frequency domain. And on the other hand, on the other side, then we have again demodulation, low pass filtering, and we arrive at the in-phase and quadrature components after down conversion, Zi and Zq. And the baseband equivalent signal of S tilde is assumed to be strictly band limited to B in our case. So it passes the low pass filter as defined here above. Yeah, we can derive the in-phase and quadrature component of the baseband received signals now using in the frequency domain, using these, we end up with these equations. So when we do the inverse Fourier transform of this formulation here, we end up with the time representation of the in-phase and then respective the quadrature component. And then the complex baseband equivalent signal can be given by the Fourier transform of Si of f plus Sq of Jsq of f. And then we have to multiply this with the ionosphere transfer function, but shifted to so f plus fc. So it's shifted to the because the effect is happening in passband, yeah. So the transfer function is related to the passband signal. Yeah. So suppose a quasi-sinusoidal signal is passing through the ionosphere. We can now see some. We can derive some interesting results. So if S tilde of t is a sinusoidal signal, and with A of t times cosine 2 pi fct plus a phase phi, and from this signal, its amplitude envelope A of t is changing slowly in relation to the frequency f of the sinusoid, and the derivative of the logarithm of A of t with the respect of t, and the absolute value is much, much smaller than 2 pi fc. So if this is the case, at the output of the ionosphere transfer function, we get S tilde f times HIF. So this is again the passband signal. If we apply now here the inverse Fourier transform, we get Z of t, and we can approximate at the output now the signal because of our assumption that it's a quasi-sinusoidal signal. We get AI, so this is coming from the transfer function of the ionosphere, AT minus tau g, yes, cosine of 2 pi fct minus tau p plus phi, where the group delay for tau v equivalent 0 can be given as, so it's the group delay Tg here is minus the derivative of the phase of the transfer function of the ionosphere divided by 2 delta f at the carrier frequency, because we are assuming a sinusoid here at the carrier frequency fc, and we get to that this derivative with respect to f is minus 40 if we apply the phase definition from beforehand, is 40 to 0.3 meters cubic divided by s square, and then here we have the slant tag divided by c f at f equals fc, and this is equivalent to minus tau I at the carrier frequency. And the phase delay, so the delay t tau p can be given by minus phi I of fc divided by 2 pi fc, and this is equivalent to tau I as we defined before. So the phase delay and the group delay of the signal, they have opposite sign here. This is important to remember when we derive this. So the carrier of the signal undergoes an apparent phase advance, while the complex envelope of the signal undergoes an apparent delay with respect to propagation in vacuum. The carrier appears to be propagating faster, while the complex envelope appears to be propagating to propagate slower than it would through vacuum. Since tech varies over time and the signal eventually passes through different paths in the ionosphere, the signal experiences variations of phase delay and group delay. And this phenomenon in satellite navigation is called code carrier divergence. Yeah. The difference in phase delay for two signals at two different frequencies, now F1 and F2, passing through the same path channel, hi of t, this is now here the time representation of the transfer function of the ionosphere, is, so if we calculate here the difference delta Fi minus F2 in phase delay of the two signals, we end up with this formula here, and we see that in the end we have this 40.3 divided by the speed of light and the S-tech, and we have the difference of F1 and F2 that we need to know. Yeah, knowing the two frequencies F1 and F2, measuring the difference in phase delay delta F1 and F2 in the receiver, we can now estimate the slant tech. Yeah, this is very interesting, and this is used for ionosphere monitoring. So if we want to understand how the S-tech is changing over time and have an idea how this is influencing our signal, we can make a measurement of two frequencies, measuring the phase delay difference, and knowing these two frequencies, we can calculate this S-tech. This is also used to calculate the ionosphere delay and we will hear about this in positioning a lot. So this means when we have signals on when we observe signals on minimum two frequencies, we can perfectly or we can correct the ionosphere effect to a great extent. And that's why all the GNSS sends signals on different frequencies. This has also other reasons, but one of the reasons is that you are capable of correcting this ionosphere effect. Yeah, I just wanted to show you what is the mapping function. In principle, this is a rule how to map the slant tech to tech, because we can measure slant tech, but we are maybe interested in what is the tech directly above us. Yeah, so you measure the ray path of a satellite. This is shown here. And we have the observer here on Earth, but we would like to know the tech value in the center or in the zenith of this observer. So we have a angle beta, and we have this, usually we have this central ionospheric point. This is in a sphere, I think 400 kilometers above Earth. And we have these two angles, beta and psi here, in order then to calculate from the slant tech using a model, the tech in zenith above the observer. And we can do this here based on the measured S-tech, and assuming that the ionosphere is a thin layer, and this is at 400 kilometers height, one can derive the vertical tech by applying this mapping function with these two angles, knowing the height above the Earth, 400 kilometers, and the Earth radius, averaging the average Earth radius with 6,371 kilometers. And then we arrive here at the vertical tech. So we use the NE vertical to calculate then from the S tech to be calculated from this slant tech NE. Yeah, and based on this vertical tag, we can, for example, create these kind of maps, these electron content maps. You can find them on several web pages. I took here the slant tag from the German Aerospace Center. There is the swakyweb.dlr.de web page, and DLR is providing these global tag maps in a daily basis. This is then the ionosphere range error given in meters. That is what you can see in the scale, in the color scale. Relay in the numbers in the top level or the top layer or top row of the color scale, and you can also see the relation to the tech in tech units from 0 to 100. And this is a case in the map. The small white dots, these are the receivers that are used to calculate the tech map. So we have all these observables from these receivers. Usually, yeah, and we can also see we have a lot of receivers in Brazil that are used to calculate this. And then based on some physics-based models, you can derive this global map of the tech. And directly from this, you can calculate your range error due to the ionosphere, which is quite interesting. You can also use these maps to correct the error in your receiver. There's many interesting facts or interesting things about that. Yeah, this is from 2011, November 11 attack map, and we can see, oh, it's very active here at 5:35 UTC. It's very active in Brazil, the ionosphere. Yeah, that's why I also choose this picture. Yeah, and it's a severe problem. You can see this goes up easily here in the region of Brazil, 15 meters of error on L1 range error, so it's quite large, and yeah. So we need to mitigate that. Yeah, in the equatorial regions, we have also an effect that's called scintillation effects, or ionosphere scintillation. So we have the flow of inversion of the equatorial plasma during evening hours, dusk, leads to what's called the Rayleigh-Taylor instabilities, RTI. And plasma bubbles cause amplitude and phase scintillations. Strong amplitude fading with deep fades of up to 15 to 20 dB are possible, and this is called amplitude scintillations. And in polar regions, we have geomagnetic storms cause phase scintillation. We have also a little bit of phase scintillation combined with the amplitude scintillation. So both amplitude and phase scintillations can cause outage or errors in positioning, loss of log, of signal tracking, or data transmission. And this is not only caused by, or is not only affecting GNSS, but all space-based services more or less dependent on the frequency. Yeah, we can see here a graph that shows the geomagnetic equator, and then also what's called the equatorial anomaly, and we can see that Brazil right fits into it. So we have here especially strongly these scintillation effects, and the polar region in green is the other region where we can see or experience these kind of effects. In blue is what is usually considered mid-latitudes. And you can already see that in the US, in Europe, most of Russia, these effects are not present at all. So this is a problem of the countries that are closer to the geomagnetic equator. That's why also these countries like the US and Europe, for their territory, they don't have to consider these effects. They are considering, or they're concerned about these effects on a global scale, but not in their territory. For us here in Brazil, this is a very important day to day. Yeah, I want to talk finally about, or not finally, but in the next section about the troposphere, and I will also present one of the troposphere models that can be used to correct these effects. So the propagation in the troposphere for L-band signals, so from a gigahertz to 1.8 gigahertz, is mainly characterized by the tropospheric delay. So we have a delay mainly that is constant within the frequency domain in this frequency range. Attenuation of L-band signals is rather small, also due to rain effects and so on, is not that prominent. For higher frequencies, this attenuation is more prominent. So when we go for 5G, 6G communication standards with high frequencies above 20, 40 gigahertz, we have to take care of the troposphere. But for L-band, this is not so prominent. This is one of the reasons also why this carrier frequency in L-band was chosen, so that you have not too high ionosphere effects, because if you would go to lower frequencies, the ionosphere effect would be growing. But on the other hand, if you move to higher frequencies, the troposphere effect is growing. So there was they choose a trade-off a little bit in the frequency, and one ended up with the L-band in the end. The delay is caused by natural gases here in the troposphere. Gases extend beyond the boundary of the troposphere at 9 to 16 kilometers above sea level. And the tropospheric effect is non-dispersive for L-band signals. That is, phase and group delay of the signal stay the same when propagating through the troposphere. The propagation speed of the complex envelope and the carrier of the signal are lower than in vacuum. And the tropospheric delay is dependent on dry gases and water vapor. Yeah, and I took here from a paper that's called Atmospheric Propagation Model for Satellite Communications. I took this graph to explain a little bit this attenuation. We can see here in the graph A on the left-hand side, on the x-axis, there's the frequency from 0 to 350 gigahertz. And we can see here's the specific attenuation by dB per kilometer. And we can see that this dry air attenuation, which is given in dashed blue, dashed blue line here, or magenta line, is we have a maximum here at around 50, 60, maybe 60 gigahertz. For the dry delay, and another one at 120. Above that frequency, the dry delay is much smaller than below 150 gigahertz. And we can see that the water vapor base delay is growing with frequency, kind of. The higher the frequency, if we have the same water vapor, this attenuation, specific attenuation, grows. And the sum of both effects is shown in the black curve. So we have these spikes at certain frequencies, dependent on the water vapor of some of the resonating components here and the dry delay. And in general, the delay is increasing with the frequency. On the right-hand side, if we have different relative humidity, I mean, yeah, then the effect of the water vapor is more prominent or less prominent. So I'm showing this here also to show what's the effect here. So these resonance, they pretty much stay, these peaks at the same frequencies, but they get less and more pronounced when we have higher or lower water vapor. Yeah. So yeah, for higher frequencies, we have to take into account a higher attenuation. In L-band, we are very much to the left-hand side, close to zero. You can see that the attenuation is very small. But if you move to 50 giga or so, the attenuation gets more significant. Yeah, propagation through the troposphere. We can also model this with a transfer function, h of t, dependent on the frequency. Then we have here the amplitude response, at. We have again, the delay of the signal in vacuum, tau v, and then we have tau t. Now, this is not dependent on the frequency because it's a non-dispersive medium for our frequency range. And for the zenith, elevation is 90 degrees with respect to horizon. A delay, zt, zenith delay. We can write that this zenith delay is dependent on the hydrostatic zenith delay. So the z subindex a superscript z and tau z w is the wet zenith delay. So we can break that up into these two components, this hydrostatic zenith delay and wet zenith delay. Yeah, where the following derivation, following like, the book of like, we can get the hydrostatic delay and the wet zenith delay by 10 to the minus 6, and then the integral over nd or nw, where nd is given here below by k1 times p of h divided by t of h. P of h is the total atmospheric pressure at height h in millibar. And we have tau h is the absolute temperature in Kelvin. So we see this depends on pressure and temperature, the hydrostatic delay, and then we have NW is dependent on the partial pressure of the water vapor in millibars, and then we have K1, K2, K3. These are physical constants based on theory and on experiments. And I've given them here and below. So there's K1, K2, K3 that you can choose. So this is already starting with a model for the troposphere delay. Sasta-Moyni's model, which is given here below, I have given the reference here, has defined the hydrostatic delay with this approximation, while the P0 is the total pressure at orthometric height, h, and we have here the latitude, which gives us kind of an idea of where we are on Earth, or we have to put in. So we see that the hydrostatic delay is dependent on the latitude. And following the model of Mendes and Langley, I gave also this paper here. We can use this model for the vapor, watt vapor delay. Yeah, and where here the PW0 is the surface partial water vapor pressure. So to calculate these two delays, we need the total pressure at orthometric height, and we need the latitude, and we need the surface partial water vapor pressure. And if we have this, we can calculate the the tropospheric delay based on these models. Yeah, how to using now these and what we also need now is these mapping functions, because we have to map from zenith delay again to the ray path that we have to, that is crossing. And now we can get here to Neil's mapping function. I gave you also here a reference. And we have a very complicated formulation for this mapping function. So we have two coefficient MH of theta here, and which is, and we have MW of theta also given here. We have a lot of coefficients A, B, C, theta, where before substituting the coefficients A, B, and C in MH, they must be corrected for periodic terms following the general formula. And then D is the day of the year. D0 is 28 or 211 for stations users in the southern or northern hemisphere. And when we apply all these mapping functions and models, we have also here these coefficients for different elevation angles. And we can use that then to model our troposphere and ionosphere, our troposphere delay. This is just an example combining several models for these troposphere effects. There are other models also, but these are very often used in the GNSS community. Here we can see now what happens when the signal propagates through the troposphere. On the left-hand side, we have the transmitter again, and on the right-hand side, we have the receiver, down conversion. In the middle, we can see the channel that we apply. Here's the tropospheric channel, so it's the passband convolution convolved with the troposphere transfer function. No. Yeah, and when we apply the down conversion, or we calculate the down conversion, apply the low pass filter, we can reformulate here everything, where we then in the end arrive with the complex baseband equivalent signal that is in frequency domain Si of f, so in the bottom, plus JSQ of f, and then the tropospheric transfer functions shifted from the passband to the applied in the passband, yeah, because the propagation effect happens in the passband. And with the models, we can derive the tropospheric delay, so tau t, and we can from the vacuum delay. This is only related to the distance. Yeah, so that was very briefly the troposphere, and we dived very rapidly into some examples of models. And now I just want to briefly talk about multipath propagation. So reflected or diffracted replicas of the desired signal. This is what's multipath. The path traveling by a reflection is always longer than the direct path. We call the direct path also the line of sight path or signal. Multipath arrivals are delayed and are delayed relative to the line of sight signal, and they usually have less power than the line of sight signal, yeah, because we have a larger distance to cover. This depends, I mean, if the direct signal is attenuated, because passing through a tree or something like this, we can have a specific we can have a specific case where the multipath signal can be stronger than the line of sight signal. This is in one of the lower bullets here explained. And in case the multipath delay is large, that means greater than twice the spreading code symbol period. So the chip duration that we defined in lectures 1, 2, and 3, the GNSS receiver can readily resolve the multipath, because then the signal is uncorrelated. So the multipath signal is quasi uncorrelated to the line of sight signal. So this doesn't hurt then anymore the synchronization. So if the multipath signal is delayed more than 2 symbols of the chip of the spreading sequence, we have no influence on the multipath anymore, quasi no influence. So only the shorter delays are relevant to the problem of synchronization in our case. If the multipath delay is larger than 2 spreading symbols, it still can affect the data demodulation. So for the data demodulation channel, we have to take into account these longer multipath signals, but for the ranging, we have usually not a problem. The direct path can be strongly, I said this already, strongly attenuated, maybe by shadowing when the direct path propagates through foliage or a structure, maybe a window. So when we think about indoor navigation with satellites, in such cases, multipath power could be even stronger than the line of sight signal. So maybe you have the line of sight signal passing through a wall, and you have a multipath signal entering through a window in a room, or these kind of things. Multipath signals with shorter relative delay with respect to the line of sight signal will be influencing the ranging performance. And I gave this here again in a power delay profile of our channel. So these errors, these blue errors with that are closer to the y-axis, they are characterizing our near echoes, while the x-axis shows us the relative delay of these echoes to the line of sight signal, and maybe the arrow right on the y-axis is the line of sight signal. And then we have also these far echoes. Multipath signals with longer delay will not influence the ranging performance, and this is what we call far echoes here. Yeah, multipath propagation can be characterized also by a transfer function. So we can use here h of m, multipath of f, and then we have here first the line of sight propagation. So we just introduce here the Doppler shift for the line of sight and multipath signals, f tilde 0 and f tilde m. And we have then here alpha is the relative amplitude of the multipath with respect to the line of sight, because the line of sight signal of is not attenuated. And we have tau m. This is the relative delay of the multipath with respect to line of sight signal. And now we can also have a look what happens in baseband again. Yeah. So when we, again, we have our transmitter on the left-hand side, our receiver on the right-hand side. The passband signal S tilde of t is convolved with the multipath channel and passes through these low-pass filters after multiplication with the square root of 2 cosine and sine terms, and we end up with the signals here after down conversion, the in-phase and quadrature components of the baseband signal. And we can do this applying again these the low pass filter H of LT. We get these 2 equations for the in-phase and quadrature signals. And then when we build the complex baseband equivalent signal, interestingly, we can see now that the channel is applied to the baseband is convolved with the the multipath channel is convolved with the complex baseband signal. And we can see that we have a time delay and a phase shift related to the time delay when we see when we talk about the multipath signals. So we have in the passband we introduced a delay of the signal, and in the baseband we see now here besides the Doppler shift also a constant phase shift that is dependent on the delay. And the delay on the signal is also introduced by this Dirac delta function t with t minus tau m. So we have a time delay plus a phase shift. So this is the end of my talk this morning on propagation effects, some comments and some basic introductions. Do we have some questions? Okay.
Signal. Well, there is a very large path to the signal between transmitter and receiver. So I would like to know if there is some power delay profile example for how much multipaths comes at the receiver. How much I'll have to worry about the multipath. I know that in mobile communications, we can usually have 8 to 15 in the usual power delay profiles. You have some example of this for satellite communications?
Yeah, there's models that you can use that they are based on measurements. As I said, you first of all have to separate between these near echoes and the far echoes. In communications, I know all these echoes have a meaning and they are considered. In GNSS, as I said, for the ranging performance, the far echoes can be neglected. So we only have to consider the near echoes. And usually there are not so many. So I recall there are several models, and they have like 4 or 5 at most echoes usually. So there's a satellite to Earth broadband model for direct sequence CDMA. Also, they considered up to 3 echoes with different statistics, and but they assume also for the echoes that they have a certain amplitude distribution also. So they assume that these 3 main echoes are a superposition of many echoes also. So in my understanding, and other models, they have 4, 5, 6 paths, but as I said, they only consider the paths that have a relative delay that's smaller than 2 chips. So when we talk about GPS L1 carrier frequency, then we have a chipping rate of 1 mega chip per second. Then we talk here about less than 600 meters of ray path or multipath extended path or increased path lengths. This is a lot. So we have to consider maybe a lot of echoes. But yeah, in the models that I have seen, the number of echoes is not very large that are considered there. Yeah.
So I have a question about going back to the slides number 26 and 28, please. Yes. It's not a coincidence that the most intense regions of TEC are the same of the tropical convergence, intertropical convergence zone, right? It's not, and I can see that in the region near, I guess, São Paulo. Yes, this region there is the same region of the South Atlantic magnetic anomaly, right?
When I go to the next slide, you can see that the geomagnetic magnetic equator has an anomaly here. So let's. This is the other slide. No, 2 slides. No. Where is this? It's here. Yeah. This is the part here where you have the bend right above Fortaleza or close to Fortaleza. Yeah. And you can see also in the tech map that the effect close to the geomagnetic anomaly is not that large, but when you move further up and down, this effect is stronger.
Thank you.
But still, it's still large enough also here because we don't leave the orange zone. So, so this is a difference between in range error of 12 to 16 meters. Yeah, so I think it's still strong enough also right here. Do we have questions from the chat, from the online audience? Okay, thank you very much for your attention, and we here will have the coffee break. We will continue at 11 o'clock today with the next expert talk. I'm happy that we will welcome somebody from the European Space Agency talking about the search and rescue service of Galileo. So see you at 11 o'clock Brazilian time, and this is 4 o'clock in the afternoon in Europe, and maybe different wherever you are. So see you later.